Hello everyone. In this session, we are going to discuss one important problem in Bode plot. In this problem, we are going to determine phase margin, gain margin, and the range of gain of the given system. So let us directly go into the problem. First, the question what they have asked. Draw the Bode plot of an unity feedback system whose forward path transfer function is given by g of s is equal to k into 1 plus 0.2s into 1 plus 0.025s divided by s cube into 1 plus 0.001s into 1 plus 0.005s. So this is the transfer function they have given, and they are asking us to draw the Bode plot. Bode plot in the sense we have to sketch magnitude plot as well as the phase plot. And in addition to this, they are asking us to determine the phase margin and the gain margin. So the phase margin and the gain margin is the basic determination of any kind of Bode plot. In this problem, one additional objective is find the range of k. So here in this problem, they have not given any specification for determination of k. So let us see how to solve this problem. So the basic things what a student need to observe is what type of transfer function is given, whether it is in Bode form or not. So here the given transfer function is in Bode form. So what is that Bode form? So always a simple pole or a simple zero that will be represented like this, 1 plus ts, where t is the time constant. So this is in that format. If you take a simple zero, this particular term, you can see the difference. It is 1 plus 0.2s. In case if you are getting the simple zero in this way, s plus 2, then you have to convert this term as equivalent Bode term by taking 2 commonly out. So I am going to pick the 2 out. So I'll put 1 plus s by 2. So the equivalent term is 2 into 1 plus 0.5 s. So this is how you have to convert the given transfer function into its equivalent Bode form, right? Then this is the first step before entering into the problem. Let us see what is the next step. So the basic thing, you have to write the given transfer function in sinusoidal form. So the sinusoidal form of transfer function is very simple. In the transfer function, wherever s is given, just put j omega in the place of s. This is what I have did in this step. So g of s in terms of g of j omega is written. Then we have to sort out the time constants. So the time constants is nothing but the coefficient of s that is present in the simple zero or simple pole. So that is the time constant. So here let me sort out the time constant one by one. So 4 terms are there. Apart from the simple basic term, we have 2 zeros, 1, 2. 2 simple zeros are there, and in this problem 2 simple poles are there, right? So I'm going to pick the time constant from these 2 simple zeros and 2 simple poles. Let me sort out that. So first one is this one. The time constants 0.2, then 0.025, then 0.001, and then 0.005. So if you sort out this time constant in descending order, first I have to write the highest value of this 4. Okay, so the first one will be 0.2, and the followed second one will be 0.025, and the third one will be 0.005, and the last one will be 0.001. Why I am sorting out the time constants in descending order? You know, this time constant will produce the first corner frequency omega c1, and this will give the second corner frequency omega c2. This will give omega c3, and the last will give omega c4. So after sorting out the time constants, our primary job is to determine the corner frequency. So 4 terms are there. So 4 corner frequencies we are going to determine. The first one is the first term, 1 by 0.2. It is 5 radian per second. Then the second, third and fourth corner frequency determination. The second one is 40 radian per second. Third one is 200 radian per second, and the last one is 1000 radian per second. So this is the basic step when you are solving Bode plot. Okay, so what I did, I have identified whether the given transfer function is in Bode form or not. Then the given transfer function is transferred into sinusoidal transfer function. Then I have determined all the corner frequencies. This is the basic step. Then the second major step is to determine the magnitude plot coordinates. So for that we need to form a table that contains the information about the corner frequencies of each term, slope of each term, slope change of each term, and the phase angle contributed by each term in the transfer function. So before that we need to assume the given gain in the system k is equal to 1. With this assumption we have to sort out the table. So in the given transfer function, as I said, we have 5 terms. So 2 simple zeros I have placed in second row and third row. 2 simple poles I have placed in third row and fourth row. And the first term will be the term, the pole or 0 present at origin. So it is 1 by s cube. So that term I have given here. That's it. So this is how I have segregated. And the most important point, it is not simply picking the simple pole or simple zero. You have to put the pole in the order such that the corner frequency should be in ascending order. You can see 5, after that 40, after that 200, after that 1000. Okay. For example, if you interchange this 2 elements, then your answer will not be correct, right? So the simple zero, there may be some confusion. Sir, which simple zero should be the second element? So you have to check what is the corner frequency. So according to the corner frequency you have to put. Similarly for the poles, there should not be any interchange between the poles and zeros. Then after forming the terms, the second column is corner frequency, and we have got calculated already in the previous step. So I can put the corner frequencies, and for first term there should not be any corner frequency. Then the third column is slope. So the slope is nothing but it is directly taken from the s, whether it is present in denominator or numerator, and what is the degree of that s. So here I have s in the denominator and the degree of s is 3. So always the s that is present in denominator will take minus 20 decibels per decade as its slope, and the degree is 3. So that should be multiplied by 3 will give you minus 60 dB per decade. Similarly, in this term, s is present in the numerator, so only the degree of s is 1, so directly I have taken plus 20. And this term also, s is present in the numerator and the power of s is 1, so plus 20. And the third, that is the fourth term, s is present in the denominator and the degree of s is 1, so minus 20. Here the s is present in the denominator, so that is why I have taken minus. Similarly for the last term, minus 20. So by this way the third column should be built, and the fourth column, change in slope. Very simple. For the first term, whatever slope you have, the same value you have to put in this change in slope. So here I got minus 60, so the minus 60 will be the change in slope. And the second term, what is the slope changes? It is the sum of the change in slope by the previous term and the present term's slope. So previous term slope changes minus 60. This should be added to plus 20. So will give you minus 40. So you have to add both this value. Similarly, in this we have got minus 40. So the next term slope change will be, you have to add this minus 40 with this plus 20, you will get minus 20. Similarly, these things, minus 20 and minus 20 should be added, and this minus 20 and this minus 20 should be added, and this minus 40 and this minus 20 should be added, right? So that will give you the fourth column elements. And the last column is framing the phase angle. We know when s is present in the denominator, it contributes minus 90 degrees angle, right? And the degree is 3, so into 3 will give you minus 270 degrees. Similar way, for the simple pole and simple zero, always the phase angle formula is tan inverse of imaginary part divided by real part. So here the real part is 1. Imaginary part is 0.2 omega. So I have taken tan inverse of 0.2 omega divided by 1 will give you tan inverse of 0.2 omega. Why this positive sign is taken? It is simple 0. S is present in the numerator. So for a simple pole you can see it is minus. So this is how you have to compile the table. After finishing the table, the next step we have to set the lower and upper corner frequency. In this corner frequency, if you take 5 is my minimum, the first corner frequency, and the last corner frequency is 1000. So I have to choose one frequency less than 5. So always it is preferable that you have to choose omega L is equal to 0.1 radian per second. And my highest corner frequency is 1000. So I have to choose one frequency which is greater than 1000. It may be 1500, it may be 2000, it may be 3000, it may be 5000. So in my case, I have chosen 2000. It is not mandatory that you have to choose 2000. It is not mandatory. You can choose any frequencies. So after selecting the lower and upper corner frequencies, next straight away we will calculate the magnitude. So first two magnitude formula always it carries the formula 20 log modulus of term 1. So the term 1 is the term that is present in the table. You can see in the table the term 1 is, this is term 1. This is term 1 in the table, that is 1 by j omega the whole cube. So I have to write this term here. So that is what given here, 20 log 1 by j omega the whole cube. And this we know log a by b is log a minus log b. So in that way they have written log 20 log 1 minus 20 log j omega the whole cube. And we know a log b square can be written as 2a log b. This cube will be multiplied with the constant 20. Okay, so that is how this term is written, 20 log 1 minus 60 log omega. So by multiplying this 3 with my 20 we will get 60. So 60 log omega. So finally 20 log 1 minus 60 log 0.1. The omega value for the first magnitude is omega L. You can see omega L I have to substitute. I have chosen omega L is 0.1. So that 0.1 is substituted and the first magnitude I have determined. Similarly for the second magnitude. For the second magnitude the formula remains same, only the place where the change occurs is the frequency. You can see the frequency, second corner frequency. What is the second corner frequency? It is 5. So 5 is the second corner frequency. So for that I am getting minus 42 dB. Using your calculator you can calculate. And from third magnitude the formula is different. It is slope change from omega c1 to omega c2 log omega c2 by omega c1 plus m2. So the slope change from omega c1 to c2, c2 to c3, c3 to c4, it will come. You can easily remember this. First one always it is omega c1 to c2 and this is first and this is second. When it comes to log you have to put the second term as the numerator and the first term as the denominator. Similarly you can see this formula omega c2 to omega c3. The first term will go in denominator and the second term will comes in numerator. Similarly for the next formula easily you can remember. So this will continue if n number of corner frequencies are present and the formula is not completed plus previous magnitude. In all the values you have to add the previous magnitude. So for this m3 I have added m2. This m4 I have added m3. For calculating m5 I have added m4. Previous magnitude should be added. Now few students have this doubt, sir, what is that slope change from omega c1 to c2? Very simple. You have to check the table and the term corresponding to the first term where you put, that will be the slope change. Okay, here I am going to show you the slope change from omega c1 to c2. So here we will go back to the table. So in this table omega c1 is 5. So the corresponding of slope change, that you can see the table, The corresponding slope change for 5 is minus 40. This is omega C1 to C2 slope change. Omega C2 to C3, you have to take this row and it is minus 20 you have to take. Then for omega C3 to C4, minus 40. Omega C4 to omega H, it is minus 60. So this column is used in the formula, right? Now I have calculated all the magnitudes for all the frequencies. Okay, so for first frequency omega C, omega L calculated, omega C1 calculated, omega C2 calculated, omega C3 calculated, omega C4 calculated, and omega H. So totally 6 coordinates. You can see 1, 2, 3, 4, 5, 6. So I have 6 coordinates. Write it, and then phase plot. So the phase plot is very simple. You have to choose frequencies between omega L and omega H. You can take n number of frequencies. For my case, I have chosen the first frequency will be omega L and omega C1, omega C2, omega C3, omega C4, omega H. So in between each 2 frequencies, you have to choose one more frequency so that you can get smooth phase plot, right? So I have chosen, in my case, I have chosen, there is no restriction that you need to choose only this. Your friend may choose some other frequency. You can choose. I have chosen 0.1 first. Next 5 is my first corner frequency. You can add one more frequency in between 0.1 and 5. You can add 2 in between. So according to that, you can calculate the phase angle. Similarly, you can add more number of frequencies. If you add more number of frequencies, your plot will be very smooth, right? So now I have 2 coordinates with me. Now let us directly go and see how the plot is plotted. So here in my case, the highest magnitude, I have chosen the scale to be 40 decibels per unit. For magnitude plot, 40 decibels per unit, and for phase plot, 1 unit is equal to 100 degrees. And the magnitude plot coordinate, sometimes you can go with 20 dBs. According to the sections, you have to choose the scale. Our primary job is to write the transfer function in the plot, then scale in the plot, then you have to draw the coordinates. Okay, now I have sketched all the coordinates. Now our ultimate aim is to determine the phase margin, gain margin, and the gain K. So if you observe, the plot, magnitude plot cuts the 0 dB line. So you need to know what is 0 dB line, what is minus 180 dB line. This 0 dB line is the reference line for the magnitude plot, and this minus 180 degree line is the reference line for phase plot. So my magnitude plot cuts 0 dB line at this particular point, and the corresponding frequency what I have measured is 1 radian per second. So this is what the gain crossover frequency. Gain crossover frequency is nothing but the frequency at which magnitude plot crosses 0 dB line. Similarly, the phase plot, you can see the phase plot cuts minus 180 degree line at 2 points. So the first point is here and the second point is right over here. So there are 2 phase crossover frequency. Phase crossover frequency is nothing but the frequency at which the phase plot cuts minus 180 degree line. So at 2 points. So the first point it cuts at 16 radian per second. Second it cuts at 370 radian per second. So 2 phase crossover frequency and 1 gain crossover frequency. Now I am going to explain you how the phase margin is determined, how the gain margin is determined. So for that you need to mention a sign convention in your plot. So the first sign convention is for magnitude plot. Always you have to mark this minus plus sign in this way for magnitude plot and plus minus for phase plot before sketching all these things. You have to fix the sign convention. So let me tell you why that sign convention and where it is actually used. So here the phase margin is the range of phase at gain crossover frequency. So this is my gain crossover frequency line. You can see if you extend this gain crossover frequency line, the line cuts the phase plot at this particular point, and the range between the minus 180 degree line and this point will give you the phase margin. So the range, you need to determine the range, just count the number of lines. I have taken 100 degrees per unit. So one line is equal to 10 degree. So here I will count the lines that is present between these range. You can see, let me highlight the range that is present in this gap. You can see this is the range. So if you start counting the line, you can see 1, this is 1, 2, 3, 4, 5 and 6th line. So between 6th and 5th line the intersection point lies. So it is 60, between 60 and 50. So I can take 55 degrees. Okay, so 55 degrees I have taken, and if you observe, this particular range occurs below minus 180 degree line. So below minus 180 degree line I have taken the sign convention here, which is used as minus. So the phase margin is taken as minus 55 degrees. If you notice this particular sign convention, the value, the role of sign convention is, this is the role, right? So similarly, I have two phase crossover frequencies, right? So one is at this particular point 16 radian and another one is 370 radian per second. So I have to extend this line to meet the magnitude plot. So that particular line intersects the magnitude plot here and here. Okay, the range between 0 dB line and the intersection points will give you the gain margin, right? So the range in the sense you have to calculate the decibels, not the point. So here I have 1 unit and some lines will be there, some 6 to 7 lines are there. So if I calculate the total number of lines, so one line is equal to 4 dB. So 4 into that number of lines will give you this decibels. Similarly, here you have to count how many lines present in this range and count that line into one line value will give you gain margin 2. So that is 104 dB and gain margin 1 is 62 dB in our case. Okay, so this is what the determination of gain crossover frequency, phase crossover frequency and gain margin plus phase margin. Now let us see the last objective, how K value is determined for this problem. You can see the last step is, it's very simple. Here they have not given any specifications to determine the value of K, but we have two ranges. You can see here the first gain margin is 62 dB, okay, and the second gain margin is 104 dB. So the gain margin formula is 20 log K. 20 log gain will give you gain margin in decibels. So I have 20 log K for this value and 20 log K for this value. Okay, so by solving this equation, you will get K range. First minimum range 1251 and the maximum range 158489. Right? So the range of K is between these two values. For this model, they have not given any specification, but you know the value of gain margin. From the gain margin, you can easily calculate the range of K. So this is all about this problem. So in this problem, let us have a small recap. In the first step, we have written the sinusoidal transfer function. Then we calculated the corner frequency. Then magnitude plot table and coordinates. Then phase plot coordinates. Then we sketched the Bode plot and we determined the gain crossover frequency to phase crossover frequency. Using the values of gain crossover frequency and phase crossover frequency, we calculated gain margin and phase margin. In our case, two gain margins present, and using that gain margin, we calculated the gain. Here in this problem, no specification is given to determine K. So directly we can convert that gain margin into K. So this is all about your basic type problem. Thank you.